This is another example of an equilibrium problem that we're going to need to use an ice table to solve. And specifically, this is an example of an equilibrium problem. We're going to take advantage of the fact that the equilibrium constant is small to simplify the problem. So, I'm going to build my ice table. And remember, we can only plug concentrations in molarity or pressures in atmospheres into our ice table. So the fact that we're given the amount of H2S in moles means that we need to convert that into a concentration first. So remember that molarity is equal to the moles over volume. So I have 0.45 moles divided by 3.0 liters. So my molarity is 0.15 moles per liter, or 0.15 molar. So I can go ahead and put that in for the initial concentration of H2S. And because they don't tell us we added any of the products, those concentrations initially are going to be 0. So now I'll fill in the change row of my ice table. So because I'm starting with reactants, I don't have any products. I know the reaction is going to go to the right. And so I think it makes sense to make the sign on the change for the reactant negative. And because the coefficient for the H2S is 2, it's going to be minus 2x. Whatever the sign I give to the change of the reactants, the products have to have the opposite sign. So the H2 is going to be plus 2x, and the S2 is just going to be x. And to figure out the equilibrium row of the table, remember that the equilibrium is always equal to the initial plus the change is equal to the equilibrium concentration. So in the case of the H2S, I'm going to have 0.15 minus 2x. I'm going to have 0 plus 2x, or just 2x, for the hydrogen, and 0 plus x, or just x, for the S2. Now, in order to determine the equilibrium concentration of H2, I'm going to plug the equilibrium constant and everything that I have in the equilibrium row of my ice table into the equilibrium constant expression. So the equilibrium constant expression for this reaction is Kc is equal to the concentration of H2 squared times concentration of S2 over the concentration of H2S squared. And so I'll put 2x in for H2, I'll put x in for the S2, and I'll put 0.5 minus 2x in for the H2S. And I'll do that on the next slide. So let me go ahead and put in the number for the equilibrium constant as well. And then for my ice table, I'm going to have 2x squared times x over 0.15 minus 2x squared. Now, this problem might be a real challenge to solve because if you look in the numerator here, I'm going to have an x cubed, and I'm going to have to FOIL out the denominator, and that's just going to be ugly. But due to the fact that the equilibrium constant is very small, and I started with all reactants, that means it's only going to go a very small amount towards the products to reach equilibrium. That means that x is going to be very small. And in particular, 2x relative to 0.15 is going to be almost nothing. And so the approximation that we can make is that 0.15 minus 2x is basically just going to be equal to 0.15. And so I can ignore the minus 2x here. And so if I rewrite that equilibrium constant expression, all right, and so to continue solving this, I'm going to multiply both sides by 0.15 squared. And so I'm going to end up with 2.09 times 10 to the minus 9 is equal to 4x cubed. Now all I have to do is divide both sides by 4, then take the cube root and end up with x is equal to 8.05 times 10 to the minus 4 molar. Now it's important to always check and make sure that the assumption that we made is a valid one. So we want to check that the change in concentration is less than 5% of the initial concentration. Let me do that on the next slide. So the change in concentration is 2x. The initial concentration was 0.15. Convert that into a percent. I want to make sure this is less than 5%. So I've got 2x is equal to 1.61 times 10 to the minus 3 over the initial concentration times 100. And I end up with 1.07%. That's definitely less than 5%, so the approximation was okay to make. Remember, the problem asked us to solve for the hydrogen concentration, and the concentration of H2 was equal to 2x, and 2x is 1.61 times 10 to the minus 3 molar.